the scale of the problem is enormous. It takes a long time to replace all power sources by renewables. We have 420 parts per million CO2 in the atmosphere. The last time we had that much CO2 in the atmosphere is in the Pliocene. It's about 3 million years ago. At the time, sea level was somewhere between 6 and 15 meters or so higher than today. You experience these intense rainstorms now that decades ago you could only glean from models would occur. Extreme positions that say, either the end of the world is near or it all doesn't matter, they, of course, get a lot of traction in the media right now.
Climate change has been a very divided subject for as long as I remember. Although I had my own strong but very much uneducated thoughts on the subject, I finally decided to interview an actual expert to have my questions answered. Tapio Schneider is the authority in the field of climate change. He's a senior research scientist and a professor of environmental science and engineering at Caltech, and you can't get any more qualified than that. We discussed whether or not climate change is a real threat, what the worst-case scenario looks like, and what actions have been or should be taken, if any. But before we start, don't forget to subscribe. And now we start. Is climate change and global warming the same thing? Or those two terms should not be used interchangeably?
I think they're increasingly used interchangeably. I mean, climate change, perhaps as the more generic term, can refer to any change that has happened over Earth history. Earth has cooled, for example, and on long time scales. And you can call that climate change. But in popular use, I think they're used fairly interchangeably, referring to the recent global warming that's ongoing.
If Earth has cooled, as you mentioned, why are we concerned about global warming, and what's the driver of it?
Over timescales of many millions of years, Earth has cooled. Over 50 million years, Earth has cooled, from the age of dinosaurs till now. Now it's cooler than it was then. But the last 10,000 years or so, Earth's climate has been very stable, and that allowed human civilizations to develop, allowed humans to settle, build cities, develop agriculture, and the like. That all was only possible because the climate was very stable, very steady for thousands of years. And over the last 150 years, we have just increased the concentration of greenhouse gases in the atmosphere. They trap heat nearer to the surface and lead to warming. And that warming is being realized right now. So we have seen just about 1.2, 1.3 degrees centigrade warming over the last 150 years. And that may not sound like much, but actually is a fairly large change if you put this in a historical context. It's much larger than any change we've had over the last 10,000 years at least.
What would be the normal range?
Temperatures vary, of course, naturally. In the global mean, there's a 0.1, 0.2 degrees up and down with El Nino, with changes in the ocean circulation. On somewhat longer time scales, there are climate changes having to do, if you think about the last 10,000 years, with, for example, changes in Earth orbit leading to warmer northern summers in the mid-Holocene than we've had now. And then if you go back in time, of course, there were natural climate changes that were large. There's the cycle of ice ages and warm periods in between. The temperature variation from ice ages to warm period we don't know precisely, but it's just around 5 degrees centigrade. So 1.2 degrees is 20% of an ice age change already, and we're about to get more.
At 5% change, we had ice age. At 1.2 is what we got. Is it what I'm hearing?
Yeah, warm period to ice age is about 5 degrees centigrade temperature difference in the global mean. And now we've had about 1.2, but of course, global warming hasn't ended. We will get more warming in the coming years and decade. I would think at least 2 degrees above pre-industrial times is probably what we'll have to be looking at. Potentially more if we don't manage to curb emissions sooner rather than later.
There is a conversation of greenhouse effect, and you mentioned greenhouses. What is greenhouse in general?
The greenhouse effect, strictly speaking, is a bit of a misnomer all in itself. I mean, greenhouses are mostly warm because the turbulent exchange of air with the surrounding is inhibited. When we talk about the greenhouse effect in the atmosphere, what we mean is that the atmosphere has gases like water vapor and carbon dioxide naturally that are absorbing thermal infrared radiation, the long wave radiation that you feel if you put your hand over a warm object, for example. What these gases do, they absorb this radiation, in some ways trap some of it closer to the surface that otherwise would escape directly to space, radiate some of it back toward the surface, and that warms the surface. There's a natural greenhouse effect that makes our planet habitable in the first place. Without a natural greenhouse effect, the global mean temperature of Earth would be about minus 18 degrees centigrade, minus 1 degree Fahrenheit. And the natural greenhouse effect makes Earth habitable in the first place. And that's mostly due to water vapor and CO2. And to that natural greenhouse effect, we are now adding by emitting greenhouse gases. And the greenhouse gases we're emitting is carbon dioxide primarily, but also other gases like methane, nitrous oxide, CFCs play a role, and the like. And all of these gases add to this natural greenhouse effect, absorbing long-wave radiation, thermal infrared radiation, emitting some of it back towards the surface and warming the surface in the process.
So ideally, we wouldn't have most of these gases, right? If we look historically in pre-industrial, greenhouses only included vapor and probably CO2. Is it fair?
Right. Water vapor and CO2 are about equally important. It's roughly 50-50 in their contribution to the natural greenhouse effect. And in pre-industrial times, we had, in the Holocene, the last 10, 11,000 years, we had about 280 parts per million CO2 in the atmosphere until the beginning of the Industrial Revolution. That's a typical value for a warm period. But now we are at roughly 420 parts per million, so 50% more than there was naturally. And that is the primary driver of global warming that we are seeing.
And how fast is that growing?
So the emission of CO2, so emission of carbon, it's about 40 gigaton of carbon per year. So if you want to put this into numbers that are intuitive, it's the weight equivalent of about 10 mid-sized passenger cars per person in the US that's added as CO2 to the atmosphere. The rate of growth it's a few parts per million year over year in the concentration in the end. And it varies a bit depending on, say, how many wildfires there are and the like.
Also, when we think about global warming and climate change, like what's the worst case scenario? What are we talking about? Are we saying that the Earth going to turn into Venus type of planet or something else?
That probably is not the worst case scenario in the nearer future, geologically speaking. So Venus had what's called the runaway greenhouse effect, where warming led to evaporation of water that once apparently was on Venus' surface. The water vapor itself is a greenhouse effect, leads to more warming, and you can get a runaway of this feedback process. But for that runaway to happen, you need to be close enough to the sun. The amount of solar radiation received from the sun needs to be exceeding a certain threshold, something called the Kobayashi-Ingersoll limit. And Earth is beyond that threshold. So we are not likely to experience a runaway greenhouse effect like on Venus anytime soon. Of course, the sun is a main sequence star. Means it undergoes the natural evolution of main sequence stars. Its luminosity, the amount of light it emits, increases over time. And over time scales of billions of years, well, eventually the sun will be luminous enough that we are beyond that limit and life on Earth will become impossible. But here we're talking about billions of years, not hundreds of years. I mean, the worst case scenario right now is, warming has, of course, the immediate effect that any heat wave will be more severe simply by shifting the mean temperature towards warmer temperatures. It also has the effect that rainstorms will become much more intense. For example, the reason here is also relatively straightforward physics that warmer air holds more moisture and more moisture can rain out in storms. That effect is fairly large. You have the intensity of the most intense rainstorms increases by about 7% per degree centigrade warming. So that's something we are already seeing. As one example, Hurricane Harvey that devastated Texas in 2017. Several independent studies have estimated that the probability of the rainfall that caused all the damage during Harvey, the probability of that rainfall occurring had roughly been tripled by recent warming already.
And people who listen to this, they might think, okay, this doesn't sound like something we cannot prepare for, right? Like Hurricane Harvey, as terrible it was, there was a ability to somewhat predict that it's coming, have that technology and move people away. Is there like second level risk to that? Like not just the intensity of rain, but what else can it cause outside of the damage, which we can technically with enough money deal with?
Right. So we have no choice but to prepare for the risks, to adapt to the risks. So I think our reaction to the reality of global warming should be two things. We need to mitigate whatever we can avoid, meaning try to reduce emissions as quickly, as effectively as we can. There is no choice but doing that. At the same time, as the Hurricane Harvey example shows, there are some changes already underway that are unavoidable. And to those, we need to adapt. And adaptation is a complex set of things that need to happen. The first thing, and the core of my work, is figuring out what to adapt to. It's one thing to say the probability of Hurricane Harvey's rainfall occurring has tripled after the fact, but it would be much more effective to have good quantitative risk assessment, say for Houston, Texas, well before something like Harvey strikes, that you can prepare the built infrastructure, houses in coastal areas, levees for storm surges and the like accordingly, that they can withstand the storms that we expect to come. Also, immediately before a disaster like that, of course, Hurricane Harvey, you could predict the track quite well at the time it occurred. The hurricane track forecasts have become quite good. Intensity forecasts are also getting better. But now translate the rainfall forecast, for example, into a detailed flood forecast. That's not very accurate at this point. So that's another area where we need better science, better engineering to have more accurate forecasts so that, for example, FEMA can place the assets in places that are likely to stay dry and enable them to reach flooded places and the like. All of that requires advances in science and engineering, all the way from predicting what is to come, assessing the risks of what is to come, to the engineering work of adapting to those risks.
You've been studying climate change for a long time. How has your perception of the risks changed over the years?
Yeah, I mean, I entered this field as a graduate student in the mid-1990s. I think I should say the perception of my risks has not dramatically changed over these soon 30 years. Of course, the risks have become much more palpable now, but what we are seeing is happening now is more or less what was predicted decades ago. So the perception has changed. You experience these intense rainstorms now that decades ago you could only glean from models would occur. But I think my perception of risks has not dramatically shifted. I think the urgency of addressing the risks has changed. It is much more urgent now to make progress, especially on adaptation measures. It's much more urgent now to mitigate the warming we can avoid by reducing emissions than it was 30 years ago. What has changed is that, say, had we figured out a good way of reducing emissions effectively 30 years ago, we would need to reduce less now. Our job now would be easier. That's easy to say, of course. I mean, the thing that really has changed, I think, is that when I entered the field, it was hard to see what the solutions would be. There was a lot of talk about behavior changes and in some ways trading economic development for a more livable planet. And that's a difficult trade-off to make in many ways. What has changed is the technological evolution has been, I think, more rapid than I expected and then probably many others expected. And now the cost of installed solar power has dropped by almost a factor 10 since that time, for example. By now, the cheapest way in many parts of the world to build a new power plant is to build a solar power plant. It is cheaper than fossil fuels or anything else. So what has changed is that there are solutions on the horizon. Realizing them is still a serious scientific engineering challenge, but they seem within reach in ways that they did not seem within reach 30 years ago.
And when we say the issue is urgent, are we talking about 10, 20 years? Or are we talking about 100 years?
On timescales of decades here, so there's no strong nonlinearity, no strong tipping point we are aware of. That you cross this or that temperature threshold, then something very dramatic would happen that wouldn't happen at 0.1 degrees cooler temperatures. There are various temperature thresholds. Say the Paris Agreement stipulates we should limit warming to 2 degrees above pre-industrial times and strive to limit it to 1.5 degrees above pre-industrial times. The 1.5 degrees are not achievable. In practical terms, 2 degrees is a severe challenge to achieve, to limit warming to 2 degrees warming. But it's important to realize that every bit of warming that we avoid matters and is important. So the question of timescales then becomes hard to answer, in that there isn't sort of the hard wall, you hit the wall and then something terribly new will happen. There's just more of the same that gets worse that will happen. So we should strive to reduce emissions as quickly as we can, expeditiously as we can, while recognizing that the technology, for example, to ramp emissions to zero right now does not exist at scale. So that needs to be developed, and the time, it will take some time to develop those technologies. And our task should be to accelerate that development as best as we can with incentives in the public sector and the like. When I say there are no tipping points that we know of for the next few decades, one thing that's important to keep in mind is that there isn't anything we know of that flips over at any given temperature threshold, but the impacts get worse with every bit of warming that we get. For example, if you look at our closest geological analog to where we are right now, we have 420 parts per million CO2 in the atmosphere. The last time we had that much CO2 in the atmosphere is in the Pliocene. It's about 3 million years ago. At the time, sea level was somewhere between 6 and 15 meters or so higher than today. So that's, of course, enough to flood many coastal areas where the vast majority of the Earth's population lives. Ice sheets respond slowly to warming, and in some ways, some sea level rise will be unavoidable into the far future, even if we figure out ways to cut emissions to zero, stabilize concentrations of CO2 in the atmosphere. Ice sheets will continue to melt for quite some time. And it's just yet another reason why it's imperative to reduce emissions as quickly as we can.
And melting of ice sheet, they definitely contribute to sea level rise, but it's not immediate, right? It's like coastal cities and countries can try to adapt by building walls or something, or pushing the city up. Is it fair? Or
for some time you might, right? I mean, the Netherlands are one example of a country where a good part of the country lives below sea level. Sea level rise has two components. One is simply thermal expansion of oceans. As oceans warm up, they expand, and that leads to sea level rise. That sea level rise is ongoing. That's dominating the current sea level rise. And that is likely going to give us tens of centimeters in the next few decades in sea level rise. Ice sheets melting, I mean, as soon as some land ice melts and goes into the ocean, it immediately contributes to sea level rise. There is no delay in that part. There is inertia in the ice sheets themselves that it takes some time for ice sheets to melt or to break up. How long that takes, we don't really know. That's actually an interesting question. In models, it tends to take centuries, but again, there is evidence from past climate changes that ice sheets can collapse quickly, and that's a concern, for example, in West Antarctica. If an ice shelf, so the floating portion of an ice sheet collapses, it buttresses the ice sheet behind it, it can lead to more rapid flow of that ice into the ocean. And there is a potential for rapid changes in sea level due to collapse of portions of ice sheets. That potential we cannot assess very well. So when I said before that we are not aware of clear tipping points at certain temperature thresholds, we do know there's evidence that ice sheets have responded at times very quickly over Earth history to climate changes. And there's a risk that this will happen again, and we cannot quantify that risk very well right now.
When we look back at historical climate, how are we able to estimate what type of climate we had? Is it like geological surveys, etc.?
Yeah, it's actually super interesting how this goes, and there are different methods on different timescales. If you look at the past million years or so, we have ice cores in Antarctica. There's ice that's several 100,000 years old. You can drill into the ice and retrieve old ice from the bottom of the ice sheets. And that does a number of things. So in the ice itself, there are little bubbles of ancient air frozen in there, preserved. So you can measure for example, the CO2 concentration in those bubbles of ancient air, as a result of which we know the CO2 concentration over the last million years or so very accurately. The other thing that you can do is look at the isotopic composition of the ice, which means there's our usual H2O with the atomic mass 1 hydrogen as a standard water. But every now and so often there's HDO with deuterium instead of hydrogen. So it's twice the atomic mass of the regular hydrogen. And the frequency with which you find these isotopes of hydrogen in ice depends on the temperature at which, ultimately the vapor that ultimately snowed down, precipitate down on the ice formed. So that gives you one handle to try to infer the temperature history of Earth over timescale up to 1 million years or so. As you go further back, there are other geochemical ways of figuring out the temperature of Earth. The little organisms living in the oceans, for foraminifera, for example, they have carbonate shells that rain down to the bottom of the ocean, and you can drill sediment cores in the ocean bottom and recover the fossilized shells of these organisms going back tens of millions of years. They're primarily calcium carbonate, but there are impurities in the carbonate shells. Sometimes the magnesium replaces the calcium. And you can look at the oxygen isotopes in the carbonate and the frequency with which different isotopes are forming the shell, or with which magnesium impurities are embedded in the shell, is likewise dependent on the temperature at which these shells formed, from which we can infer ocean temperatures going back tens of millions of years. And then in more distant past, the last few thousand years, 10,000 years or so, a bit more, you can look at a variety of other indicators. For example, tree rings. The width of tree rings depends on temperature, water stress, and you can infer temperature history from tree rings that way. So if you think back, we are in California. I don't know if you have been to the bristlecone pine forest in the White Mountains. I recommend to visit. It's the oldest living organisms on Earth are there, 4,000-year-old trees, bristlecone pines. So they encode 4,000 years of climate history in their trunks, and we can use that to infer more recent climate changes.
What causes this disagreement on climate change issue? Because you have people, I think they have several groups of people. One say there is climate change, we need to deal with it immediately. The other one says there is no climate change. Third one says, well, there is climate change, but it's not as urgent because it takes thousands of years for us to feel strong repercussions. What's happening?
I mean, it's an interesting question of how our discourse in general has become more polarized over the last few decades. If you look at the climate change policy history, we have the United Nations Framework Convention of Climate Change, which was passed in 1992, the Earth Summit in Rio. President Bush signed it. The Senate at the time ratified it. This is the framework for Paris Agreement, Kyoto Agreement, all the follow-on agreement that came after. It stipulates that we should avoid dangerous interference with the climate system. It stipulates that we should gather and share information on greenhouse gas emissions, national policies, best practices, and the like. At the time, President Bush declared that the United States intends to be the world's preeminent leader in protecting the global environment. There was a clear notion of we need to be good stewards of Earth. It was ratified by bipartisan support in the Senate. That was 1992. We've had various bipartisan efforts in the US for climate bills. McCain and Lieberman proposed an act in 2003. Lieberman and John Warner, Republican from Virginia, proposed an act in 2007. This seems inconceivable now, right? That there is a Republican president or Republicans in Senate putting forward climate legislation. These were cap and trade bills, for example. Our discourse has become more polarized, as a result of which these kinds of misconceptions that you mention have, in some ways, they've always been around, right? There's nothing new about misunderstandings about science, but they have found outlets in which they can be strongly amplified. Why exactly that happened is difficult to say. I mean, it makes sense to think that the more fractured media landscape, social media and the like, help amplify extreme positions on either end. And people then can gravitate to, in some ways, echo chambers where their preconceptions are being echoed and amplified. That is true not just for climate change, but it seems across the board for public discourse. It's difficult to say what to do about it, right? I mean, we as scientists, I feel my obligation as a scientist is to give the best possible science, which means explain what we know about climate change, as we discussed, but also say what we don't know. There are many things that are quite uncertain about the science of climate change. They don't mean that you shouldn't worry about climate change. I think to me, they mean we should redouble efforts in the science of climate change, that we know what we have to prepare for, what is coming. But extreme positions that say, either the end of the world is near or it all doesn't matter, they, of course, get a lot of traction in the media right now, and sort of a more nuanced view in the middle that, yes, it is a big deal. We need to do something about it. But we can do something about it. There are technologies, and we are developing technologies that will help mitigate climate change. We can adapt to some climate changes, at least in the developing world. Of course, adaptation is a lot harder in places with fewer resources, where you can't easily build levees, as you mentioned before. But there are solutions, and there are serious science technology challenges, and there are serious equity challenges between the global north and south, for example, where clearly global warming is primarily caused by developing countries, primarily in the north, and the most severe consequences will be suffered by the people living in places that are not the primary cause of climate change. So those are all issues we have to address. I wish we could do it in a deliberate discourse that focuses on facts and acknowledges uncertainties rather than gravitates to extreme positions that are not supported by science.
Can you elaborate on the North and South, like which countries are cause it primarily and how it affects the South directly?
The primary emitters were, of course, historically United States and Europe, and China is now the main emitter of greenhouse gases. If you look at cumulative emissions, it's primarily developed countries in the global north. And we are feeling the consequences too. For example, Hurricane Harvey is devastating in the US too. But of course, we have also more resources to adapt to the ill effects of climate change. In a place like Bangladesh, as one example, you have well over 10 million people living within 1 meter of sea level. So sea level rise there can easily be devastating without resources to adapt to. There's sea level rise on the coastal side. They also have to deal with intense rainfall, intense monsoonal rainfall that causes severe flooding, mudslides, and the like. And it's affecting millions and tens of millions of lives of people who are not living in a resource-intensive way, who are not causing global warming primarily, and yet suffer the consequences.
Do you see global existential risk from global warming, or it's more of the going to be significantly costly, particularly to poor countries because they cannot adapt? They don't have ACs to deal with the heat waves. They don't have resources to build whatever walls to protect against sea level rise or some other stuff. I'm oversimplifying, but in general, what's your take on that?
I mean, existential risk in the sense, will human life on Earth be wiped out? No, that's not going to happen. But there are still very serious risks, also because of the inequity of impacts. In countries where you cannot adapt with the coming changes, migration is an almost necessary consequence, right? And that, of course, causes geopolitical risks, geopolitical upheaval. We will probably be facing mass migrations in several parts of the world that will cause strains on all systems we have. So there are serious risks. It is a serious problem that will require serious effort to deal with on all fronts, geopolitically, mitigation, adaptation. But we have no choice but to deal with it. It's not a risk in the sense you asked before. A runaway greenhouse like on Earth, will Earth become uninhabitable? No, that's not going to be the case.
When it comes to the solution, what should countries do on a macro level, and what can individuals do on the micro level, if it makes sense?
I mean, first and foremost, we need to find ways of producing energy without emitting carbon dioxide, so carbon-free energy. There is great potential in solar power, for example, wind power where we have it. And as I said, these are the cheapest power sources in many parts of the world already. But deploying them at scale is still a challenge. You need to electrify everything. That's an infrastructure challenge. And building grids that can handle the load, can distribute the load. Of course, the challenge with solar power is that it's produced during the day and you need to deal with a storage problem, a distribution problem. Those are serious technological challenges that we need to tackle very quickly. I said there is no temperature threshold where something dramatic happens in the next few decades, but it still means we have to act quickly. And you need to keep in mind that the energy systems we have, for example, were built over close to a century, and building an infrastructure of that scale on a time scale of 20, 30 years or something like that is an enormous challenge. It requires, I think, close cooperation between the public and the private sector. It requires public incentives that incentivize transitions here. And it clearly requires private partnerships to build the technology at scale that we need here. As far as climate change is concerned, what is happening, my view of that hasn't changed all that much in the last 30 years. But of course, had there been stronger incentives in place 30 years ago, the task now would be less challenging to mitigate global warming that, say, exceeds 2 degrees or so of global warming beyond pre-industrial times. So on a macro level, I think public incentives are helpful. Of course, the global energy market is a several $1 trillion market. I mean, there are wonderful private incentives. You'd get rich if you find solutions, technological solutions to these problems, and it's good that those are in place. On an individual level, it is a bit more difficult, right? Individual action, I think, is good, and I think is necessary. But you, in the end, need solutions that scale to 7 billion people on the planet, and you individually can avoid unnecessary carbon emissions. Those of us who are more affluent, we can electrify our homes, reduce flying and the like. But it's important to keep in mind that we need a 7 billion people solution that scales. So I think it's individual actions of that type are good, but they will not scale to the planet. We need ultimately technological solutions at scale, produce energy without emitting carbon, and that usually means produce electricity and then try to convert electricity into everything else we need.
So electric vehicles, you can see them all over the place right now, right? So basically they're good to have, but it doesn't sound like they make a lot of difference because they're primarily here in developed countries. I
mean, they do make a difference. If you drive an electric vehicle in California, given California's power mix, the emissions per mile are roughly 1/5 of internal combustion engine vehicle. It does matter, even taking into account the resources needed to build batteries and the like, so the lifetime of the vehicle. But yes, I mean, you would need electric vehicles at scale right now. It's capital intensive. People who have the resources can buy them, and that's good. But it's not yet at scale and reliable at scale that everyone could use them. And well, it's a question whether we want individual vehicles. Of course, mass transport is inherently much more efficient. So it would be good to build out mass transport that's energy efficient where we can, and reduce the reliance on individual transport and the like.
I think one thing I keep hearing that even though people now can move to electric vehicles, they using electricity that was developed with carbon, right? It's almost like
Right.
What's the solution there? And what's your take on the nuclear?
Yeah. So, I mean, of course, the carbon intensity of an electric vehicle depends very strongly on the carbon intensity of the power mix that you use to charge it, which is why I said in California, for example, it's fairly efficient, and other parts of the US, say that relies more on coal. An electric vehicle gives you less of an advantage. Nuclear power, I think it's a viable stopgap measure because we know how to deploy it. We can do it now. It's not scaling to the planet. There simply isn't enough uranium around, or easily accessible uranium around, to power the planet with nuclear power. Maybe you could with breeder reactors and the like, but they create proliferation problems and in itself are a serious concern. But say if you look at countries like France that have deployed nuclear power for decades at large scales, they have relatively low carbon emissions for the entire electricity generation. And of course, there are issues with storing nuclear waste and the like. There's safety concerns, but it's important to keep in mind that burning coal has probably more serious adverse health effects right now than using nuclear power, both in terms of the coal mining to the miners and the pollution it produces. That air pollution kills millions of people per year. Thinking about nuclear power, one needs to balance it against the alternatives, and against the alternatives, it's I think a viable stopgap measure.
It almost looks to me that the biggest issue here is incentives, right? It's basically developed countries are the ones who produce the most of the emissions and cause the most of the issue here. But in order for us to reduce it, we have to accept some inconveniences which we don't really want to. Is it a fair assessment?
Yeah, I mean, that has been the tenor. And definitely 30 years ago, everyone would have said you need to accept some curtailment of conveniences, lifestyle. I'm not so sure that's still necessary. Again, the key thing here is that the cheapest way to produce electricity in most of the world right now is with solar power for new installations. And the hope would be that if you can scale those technologies, that you can have both a healthy and good lifestyle, and even healthier, much healthier than we currently have, simply because carbon-free technology is also reducing air pollution while transitioning to a low carbon or no carbon way of energy production. It would be nice if you can have it both ways. There are some areas where I think transitioning to low carbon is going to be taking longer, that are important for global welfare. I mean, take the Green Revolution and the availability or larger availability of food for the world's population over the last 30, 40 years. It was largely made possible by nitrogen fertilizers and the wide use of nitrogen fertilizers, which are produced using natural gas for the most part. We have no technology to change that right now. And you wouldn't want to, I think, say, well, we'll just stop producing the fertilizers, and as a result of which we're back to having many more people going hungry. That seems not a trade-off anyone will want to make. So there are some areas that will be harder to decarbonize, where I think we'll have to accept some carbon emissions for some time. But the hope would be that in many areas we can decarbonize the economy without doing things that people would perceive as inconveniences.
So if it's cheaper to produce through renewable energy, why don't we do it?
It's happening, right? I mean, say in LA where I live, it's if you go towards the Owens Valley, a little bit north of here, Desert Valley, There is a proliferation of solar power plants that were constructed there, largely because that was the cheapest way to supply power to Los Angeles now. But again, the scale of the problem is enormous. It takes a long time to replace all power sources by renewables. As long as solar power is supplying some relatively small fraction of the total, the problem that there is none produced at night, for example, is not a serious problem. As soon as it becomes a large fraction of the total, the storage problem is becoming a serious problem. As soon as everyone drives electric cars, everything is electrified, we need electric grids that can handle a very different load from what we are currently having. And it will just take time to build that out. But it's starting to happen. We all wish it would happen sooner and faster, but the process is underway.
And when you look back at 30 years, said people were more receptive back in the day. But now when you look at what's happening at this moment, are you optimistic? Like maybe they were more receptive back then, but they didn't have technology that we have today.
Yeah, I think I'm generally optimistic, mostly because of the advances in technology. Also, I think the public discourse clearly has changed with respect to climate change. There was a lot of concern, interest in climate change in the 1990s when I entered the field. It faded a bit for a while thereafter. It wasn't much on the public mind, but it clearly is right now. And I teach at a university. You see students starting now, for them, climate change is the defining science and engineering challenge for their generation. They approach the problems with interest, urgency, enthusiasm, and it just gives a lot of hope of the generation of those who are young, of the changes they can effect.